So, we'll continue this lecture with one person less. Here, similar to the last lecture which I held, I would like to show a simple example about, so what did we discuss until now? Well, we discussed that we want to use semiconductors to generate a lot of power. To do that, we require these materials, what are called high bandgap materials. High bandgap materials, we defined anything that has a bandgap of around 1.4 electron volts till 2 electron volts. Above 4 electron volts, it's already an insulator or considered an insulator, or not considered a semiconductor. What does that refer to? It refers to basically the amount of energy that a carrier in the valence band has to absorb in order to move to the conduction band, the band gap. Thus this 1.4 till 4 electron volts. We wanted these materials. Why? Because these materials have the property that we're able to apply a larger drain source voltage on them. And because we're able to apply a larger drain source voltage, and because they seem to have a higher carrier capability or seem to retain the carrier mobility of their predecessors like silicon carbide, or of, for example, the application of GaN or gallium arsenide or something like that. They seem to retain the mobility. They seem to have a higher band gap, allowing us to produce a larger RF output power. Now, when we said with producing larger RF output power, you have the thermal resistances, you have a lot of heat sources, because a lot of the power that you give to the device, DC power, is being lost, and lost means it's going to heat. And for that, we think about the packaging. Now, as I said to you, nowadays, you can also have, when you design such amplifiers, when you sit in when you work and you go to work to design such amplifiers, you will, if you're designing high power bars, so these high power capable devices, then you will obviously use ADS, what is shown here right now, and you will obviously make use also of CST, this 3D EM simulation tool. Now in CST here I have one simple example of a Doherty. A Doherty is a power amplifier which operates with a higher efficiency, both in full-scale application, meaning the required input power is present, and back-off application, which means the required input power is not present, but you're working with 10 dB less. So to the power of 10, hoch 10 less, or factor 10 less. So in order to, anyway, this is just a type of amplifier called the Doherty amplifier. It is irrelevant for this part here. What is relevant is these packagings. As you can see, these are the packages that I described beforehand. This is where the transistor comes in. As we've seen, the transistor that we saw. Let me show it again. We saw here. Here, you see this foil here, no? This look here of this thing looks very similar to this, right? Here's this packaging, and this is how it actually looks then in the end, you know? You have here a certain package for the die, for the transistor bar. This is an example of the transistor bar. The transistor bar is later on added into ADS. So you basically have a 3D structure that is a vacuum only, just to hold space there. And then you have a transition port definition. You can see the port definition here with regard to, from the top of the conductor. This is the gate pin. As I said, we have these capacitances that are induced due to the gate and the drain pins. And the gate and the drain pins, oops, falscher Knopf. Yep, now we're opening something we don't want to open. The gate and the drain pins are with these feeding structures, as I mentioned. The feeding structures and everything are required to contact the transistor, and from there on we add capacitances, we add undesired thermal resistances, we add a lot of undesired prospects, but we need to be able to contact the transistor finger. And so we have this representation of the transistor bar, where you have a lot of fingers here, and we can see there's bond wires that connect. And this is with respect to as we said, the input matching is relatively, whatever the input matching is, it is not the input matching that is required for your device. Thus, you have an network, LC network in this case. The L is taken from the inductance of the bond wires, and the C is taken from this metal insulator metal capacitor. So basically, there's a metal on top, insulator on the middle, and the metal downwards. And this LC network is taken to do a transformation, so to transform the input impedances to a target which you would like to see. And in the output, you connect it as soon as possible to the drain bias in order to increase the efficiency of the device. So you want to have your drain bias as close as possible to your transistor. If you have it further away from the transistor, you will decrease the operating frequency. You will also decrease the efficiency of the device. So you have it as close as possible to the device. This is a bias T. Then later on in ADS, you connect then this microstrip line to a separate LC network, to an RF shunt, and so forth, to be able to have the respective bias that you need to apply to it. This is the gate bias, the drain bias. As I said, you need bias to apply to it, bias voltage. And then you have the respective matching networks. So this, what they do is they transform your impedance to what you want to see here at the input port. And this is then how a amplifier looks actually when you want to use it for high power. This one operates at 3.5 gigahertz, for example. And you have the passive components. So you have the packaging and everything. And all this packaging, not only can it be simulated EM-wise, so you simulate the S parameters mainly of the device, and mainly, but you do generate S parameter files from this. You can also define a thermal source and a thermal sink. And you can even simulate this to be a thermal simulation to see where the spread of the heat is going on. And that, how you do that is that you define this device not only as a vacuum, as I define it here, but you define it as a heat source. And you define the respective parameters from one measurement. You have a certain technology that you can access to. In that technology, you probably have certain information about, with respect to gate width, how much thermal load is produced, when the respective biases, when the respective voltage bias is applied. You input that information into the solver, and you tell the solver, hey, I generate this amount of heat, and then you define your packaging as the sink. So what is the sink is everything that is metallic here. For example, this metallic part, the downwards metallic part, this is also like a metal. So basically the PCB board, there's one single layer of PCB board is placed on this metal plane because you want to use this metal plane to dissipate as a heat sink, to manage the heat of these devices. What is then done with this information? This information is then integrated into a separate program, which is ADS, which you probably all know or have seen. ADS is this schematic-based simulation tool. Right now, I don't have all the packages included, so the columns and everything is grayed out because they don't see the reference they need to. But what in the end of the day it is basically the representation of what we saw as a model, 3D model, with schematic components. And here, then you integrate a power amplifier, and then you can include the complete simulation of the passive components in ADS. In this case, it is not done, but in other cases, you can just include it like here, as seen with these S parameter blocks, and you can run the simulation. And this is the most realistic way of simulating both temperature development, of simulating both RF performance and so forth of the device, and how really design is done. This is how you work as a designer. You see this, you operate in ADS, you design it with schematic components, then you lay it out. The laid out file is then simulated in CST, as we see here. You take your layout, you simulate in CST, you have your packaging integrated in CST, you have your matching and so forth integrated in CST, and then you take this CST information back from here, you input it into ADS again, as can be seen, for example, here with these S parameter files, and the simulation can then run in the most realistic fashion. And what is this? What is the effect of a Doherty, for example? What does the Doherty do? And then we see here some parameters which we'll see also late now in the subject and the lecture. Oh, if I could move, that would be great. Depends on what you wanna, what the thickness of your substrate is, and where you want your application to move towards to. If you want something that is concretely in this case, for example, why I used here microstrip line is that I have a a layout, a matching layout, which has a lot of bands here and gets close by to the other subject and so forth. I'm trying to hit impedance targets and transform to impedance targets and to make it as compact as possible so that I can have a lot of these next to each other processed. And when you make that as compact as possible, compact and coplanar doesn't go together. Coplanar is usually a very wide range of operation. Sure, you can reach a lot of impedance points by being independent of the substrate. True, you do a not a grounded coplanar connection, but a non-grounded coplanar where you use the reference as your ground side, and you can, by varying the distance of your ground, your virtual ground, with respect to your middle carrier, you can achieve a lot of impedance points, which maybe with a microstrip line you will not be able to achieve, because the microstrip line, the impedances that you see are not only dependent on the width of the microstrip line, but also on the height of the substrate. But the benefit of the microstrip line is that it is one carrier which you can meander around. And the coplanar wave is basically a three carrier medium, which meandering around is very difficult. So doing these compact designs becomes fairly difficult, and the world is moving towards doing compact designs, integrating everything, integrating the antenna and so forth, as I showed you in the last subject, where the multiplier, the power amplifier, the antenna were all integrated into one single chip. And in order to achieve that, you have to use a matching technology that isn't as rigid as coplanar wave. So that's actually the actual factual view why in this case it is a microstrip line. But yes, you could also make it in coplanar wave, and most likely in coplanar wave you will have less losses, because your main wave is not perforating only the substrate, but it's half of it is across the air. Here we have a lot of the EM, basically the microstrip line mode mainly generates an E field across the substrate, and the losses are in that case then higher. But you convert that by being able to make it as compact, as short as possible. And if you make it compact and short as possible, you have less metal, meaning that you'll have less losses in the metal itself. So you can compensate the fact that, yeah, it's a game about making it compact. And in order to make it compact, microstrip line is far better than coplanar waveguides, or strip line, for example, as well. Let me go back to what I wanted to say, is that once you have that simulated, you can simulate something like this, which is the PAE, the power added efficiency of the device. You can simulate the output power of the device. For example, how much output power do we have? This is to the right then. The output power is, for example, at over 30 dBm for this device, or a peak of 35 dBm and something like that. And the efficiency goes in around 60%, but the efficiency is not only 60% for the peak application. Normally, how the normal transistor or normal amplifier would, power amplifier would behave, is that the efficiency is peak at the maximum input drive and then goes down linearly and to very low levels. But what this device does is that it retains a high efficiency, around over 60%, across a wider range of operating input drives. For example, from 35 dBm input to 28 dBm input, you have above 50% efficiency. This is just the property of the Doherty. It doesn't mean anything more or whatever. It's just a type of amplifier. But with this kind of applications, you can design amplifiers. You can check out the efficiencies of the amplifier, which is basically the efficiency with regard to the RF power, the output RF power with regard to the input RF power, and the DC power that you put into the device. And then you can check out important factors such as the matching of your device, how well your device is matched. You can plot it in the Smith chart. You can see how well your device is, what is the efficiency of your device. What is the stability of your device? Is your device stable? What is your K factor, which we'll learn later on in the subject, what it identifies as a maximum available gain, maximum stable gain, and so forth. The plus of these can be plotted in all in examples such as this. We'll proceed with the lecture. So we said modifications were done to silicon-based, or need to be done in order to achieve higher power. An example of that is this laterally diffused metal oxide semiconductor example with the with the doping with the added p doping in the around the drain gate contact, so that you have a more controlled E field, so that you can apply higher voltage. That is aided by adding this shielding of the gate drain contact, and so forth. We talked about the importance of having an input matching inside the packaging, and you saw the input matching inside the packaging, as we see in the example here, where the transistor here already sees an inductance and a capacitance and a transformation with respect to the input part, and the output part is as soon as possible on the outside to the drain, and then the matching continues here outwards. We talked about the temperature distribution, the importance in that, and the respective channel temperature, which is dependent not only on the device but also on the packaging of the device. So you not only have added thermal resistances due to the device only, but also due to the packaging that you apply to the device. We talked about higher bandgap materials and what are the properties and what polarization effects are used to achieve this 2-DEG layer, which then acquires you a high carrier concentration, carrier mobility, to be able to generate a lot of RF output power. The comparison of what a higher bandgap material versus a lower bandgap material does was at around 1.4 electron volts, as I saw here, if I'm not mistaken. And then you have a GaN, which is at around 3.5 electron volts for the bandgap. And you can see that already the output power is far higher at lower frequencies, because the problem here is the higher the bandgap, the lower the mobility. The smaller the bandgap, the higher the mobility. What does that mean? Higher mobility, high frequency capable, but low power. Higher bandgap, low frequency capable, but more power. Now we will go to more in terms of RF circuits and amplifier design. And I showed you with the amplifier design, I showed you an example of how modern amplifier design is done using EM modulation, electromagnetic simulators, and 3D EM simulators, and then ADS, which is a schematic simulator where you can put the schematic components and the respective 3D models, integrate them. We saw solutions or some results which were plotted. We saw efficiency, we saw this factor called K, which is the stability factor, and so forth. We will move on with some parameters. Something like voltage amplifications, which is AV, which is the output voltage versus the input voltage of a device, of a amplifier, or a low noise amplifier or high power amplifier, however the case, a power amplifier in this case. Current amplification is defined as the output current versus the input current. So very, very simple terms. What is the voltage amplification of a power amplifier? Output voltage versus input voltage hoop. You have a sinusoid signal driving in RF power. You have a sinusoid signal coming out. You measure the voltage hoops, the difference between the output voltage hoop versus input voltage hoop, the difference between the input current hoop versus the output current hoop. Power amplification is then basically the RF power that you put in versus the RF power that you put out. From that, you define aspects such as transconductance, which is the output current, which is the gate source voltage, or you have the output conductance, or the GDS, which is the output current versus the output voltage. We have parameters such as the Smith chart, where you can define your reflection coefficients, input and output reflection coefficients. As can be seen on the right side, you have your input, your output and input impedance, and usually in our case, what happens is that it has that the devices, these HEMTs, these high bandgap materials will have a high input impedance at the lower frequencies, and then as you move with the frequency, you will have a lower your input impedance will have a transition between higher input frequencies towards lower ones, and you will have this issue of like you move from a capacitive to a more inductive property. The similar thing is done with the output impedance that has as well has a finite output finite value. It doesn't go to infinity, but has a finite value which then moves towards the capacitive portion. So they both start at the edge. The input impedance starts at infinity and then moves towards the 0 point, or moves towards a value which is lower with higher frequency operation. And the more we are at the higher frequencies, the lower we'll have. We saw that the problem was then when we designed power amplifiers operating at 60 gigahertz or 90 gigahertz or whatever, they had an input impedance at 5 ohms plus J20 or something like that. And then you need that 5 ohms plus J20 to transform it to 50 ohms. So you need from this point here, you need to jump to this point back here, which means you need to do a lot of transformation steps, and a lot of transformation steps means you introduce a lot of inductors and capacitors and inductors and capacitors, because what are you doing? You're going up with an inductor, you're going down with a parallel capacitor, you're going down with up with a serial inductor, you're going down with a serial capacitor. You're jumping around in this Smith chart here, and every jump that you do introduces you parasitics, and with every parasitic that you introduce, you reduce your operation frequency. So you're balancing somewhere like how good am I matched, how much power can I drive in, how much power can I take out, but in what frequency window can I do that? And usually if you're operating at 0 gigahertz, you have a very high input impedance, but this input impedance travels around the capacitive portion, becomes inductive and reduces heavily. It becomes very small. The same with the output capacitance, but the output impedance has a defined point, maximum defined point, and then this maximum defined point also travels around. And you need to do these transformations from there back to 50 ohm, because we take 50 ohm as a reference impedance level where we define our usually 50 or 75 ohms are traditionally taken as a reference level where you can buy components off the shelf and then combine them. Just going to check if the recording is going. Oh yeah, very good. Continue. Yeah, this is an example of a 50 ohm medium. Now, the gain that you achieve, or the respective gain characteristic, I'm going to see if I have something here. I have the power added efficiency. I don't want that. I want the gain. You can see that the gain of the device, right? So this is the plotted gain of the device, the plotted gain of this amplifier that I showed you, of this Doherty amplifier. So it has around 16 dB gain, and then it goes into, at some point it goes into saturation, and then it goes into compression. So at some point the device doesn't have any more gain because you're driving the device into compression. Now this plotting this gain you will be, this is characteristic to where, in which stage are you in? Are you in the maximum available gain? Are you in the maximum stable gain? What is here plotted as well in this dotted line is the maximum stable gain, for example, for the device. If you go, what does that mean? Is that if you have a device which isn't operating in stability, isn't starting to oscillate, you could, as long as the device isn't starting to oscillate, you have a certain maximum theoretical gain that you can achieve. At some point, you might exceed this value. You will go below the stability factor, which is absolute stability for the device, and then you can achieve higher gain levels. But the issue is that at some point, or immediately after that, you might go into oscillation. Because you will have a spike of gain, for example, something like here, where the stability is dipping down. If you look at then in this part of operation at 0.5 gigahertz, then the device will start to be problematic, because you'll probably have a spike in gain, and that spike in gain will introduce you in oscillation and so forth, and make your device unstable. So you have these terms. This is I out versus I in. This H21. So it is the output current versus the input current. It is basically defining you the maximum current gain. That is defined by Ft. Ft says this is the maximum current gain. Fmax says this is the maximum unilateral gain. These MAG, MSG say this is the maximum available gain, and this is the maximum stable gain. After this point, you will have the gain at this point will be under the K factor, and the K factor is what we define stability of amplifiers. A simple factor to a very simple factor to define ability. But what was important in this graph here is basically this Ft and Fmax. Ft is defined by H21 when it reaches 0. So unity, gain of unity, a gain of 1, and that is when output current versus input current. That is defined as Ft, or the maximum current gain, and then Fmax, you have your maximum available gain for the device. Usually the maximum available gain is higher than the maximum current gain, or they're at the same level. It cannot be the opposite. How are these values defined? They're defined with respect to these incoming and outgoing waves. I think you've already done this with regard to S parameters when you did the two-port analysis with Professor Cry. So you're quite familiar with what is a reflection coefficient at the source and what is the reflection coefficient at the loads, and the voltage waves that go in and the voltage waves that go out, and with respect to what is the matching of the device. With these, you can define, this is how basically such a plot looks like, with and how it develops over the respective frequency. So in the lower part, you have the frequency plotted. In the right part, you have the right axis, you have the K factor, and we'll then know how we derive the K factor. In the left part, we have the MSG, MAG, maximum stable gain, maximum available gain. That's how you can define your maximum gain of a device, of a transistor. Usually, if you buy or if you want to design a transistor, you have a technology, and you have a certain node that you have access to, and these certain nodes, you have certain transistor gates that you have access to, and these transistor gates are plotted and charted in such a manner that they tell you what is your maximum stable gain, what is your maximum available gain, and with respect to the K factor, with respect to frequency. The K factor defines your stability point of your device, of your amplifier, and this K factor says if your device is above 1, it is stable. If your device is below 1, it is not unconditionally stable. So it has above 1 is unconditional stability, under 1 is not unconditionally stable. So it can happen that your device operates perfectly fine, but it can happen that your device starts to oscillate at a certain frequency point. Why it starts to oscillate is that at some frequency point, you get either a feedback loop due to having a wrong impedance target. Your complete wave gets reflected back. It gets reflected back by then the output of the trend. So you have a block. You have a two-port device. You try to push in a certain frequency from inside or from the outside. Usually it's output simulate. For example, you output instability or output oscillation. You try to drive. You try to push in a wave on the outside. It gets reflected back. gets re-amplified, gets pushed then back to the outside, gets reflected from the outside, because you have a certain mismatch in load that only 10% of your energy gets transmitted out the outside, but the rest gets reflected back, and so forth. So you have this point where you're ringing, you have a standing wave which just amplifies in amplitude, and once it reaches a certain amplitude, it burns out your device. The K factor is just a means of plotting whether this. So if you're designing then an amplifier, you've done with your amplifier, you're happy with the results, then you plot something like this, the K factor. And in this case, you plot the K factor with this kind of formula. You take the S parameters and the magnitudes. And we will see the formula also in the files, and you plot it across the frequency, and you look at where your circuit could be unstable. And in this case is a perfect example of where the circuit could be unstable. Namely, it could be unstable in the lower frequencies. There it seems to see a impedance points where the device could most likely have stability issues. Anything below the 1 point is this. There's no unconditional stability for you defined, and this unconditional stability is then in the maximum available gain insertion. Maximum stable gain is defined as the absolute value of the S21 versus the S12. You know the S21, the spectral parameters from with regard to output versus the input versus the output. So the ratio of the voltage waves that enter the input port and exit the output port. So A1 versus A2, and the ratio of the B1 versus B2. So if you say A1 is where I'm entering, I'm the amplifier, I'm taking some energy, that's A1, I'm voltage wave, and I'm exiting a voltage wave A2, then the ratio of A2 versus A1 will be my S21, and my S12 will be the opposite. If I'm taking B1 and I'm raising B2, you have just the relationship to these voltage waves. The MAG is then the maximum available gain comes into the formula comes this K factor, the stability factor, and the stability factor is defined as seen below. Sorry, as seen in this case, the stability factor is a relationship of the S parameter. So the relationship of how much of your energy wave is being accepted by the transistor, how much is being reflected away, and so forth in this constellation. This formula is something that you probably is good to know for the exam. It is good to know for the exam how you plot this, the MAG, MSG, what kind of slope it has, that it has 10 dB per decade and then 20 dB per decade here. What does it say here? What is the FT? What is the Fmax? So these kind of characteristics. You should know what the K factor is, how it is derived from the S parameter matrix, what does FT mean, what does Fmax mean, what kind of properties there are, what is maximum stable gain, what is maximum available gain, by what kind of slope does it have? Does it have 10 dB per decade, 20 dB per decade? What does it mean to be above 1 for K factor? Is it unconditionally stable? What does it mean to be below 1? It's conditionally stable, meaning that your device might oscillate and might produce these kind of information should be known. How do you derive the MSG? How do you derive the MAG? These simple formulas. What is the unilateral gain? And the unilateral gain gives you what? It gives you the Fmax. The H21, which is the I out versus the I in, gives you the current Fmax. The FT, which is the current gain, and this is the unilateral gain, which is the Fmax. So at the point where your gains, FT and Fmax, are the points where your gain is unitary, meaning that you do not have any benefit of pushing power into the device and getting out. Your power amplifier does nothing. It doesn't give you gain. It just wastes your provided DC power. So that is the part. A simple example, the role factor. There's a short wrap up. The analysis of an active device. So you use MSG and MAG. Once you're trying to define a power amplifier, whether it is pre-matched or unmatched, whether you're using a power bar from a certain technology that you have access to. You use the MSG, the MAG, the K factor to define the basic properties of that. How much gain do I have? What is the available gain that I can achieve? What is the stable gain that I can achieve? Where at what point will I have instability issues? And then you plot that in ADS, where you do the mostly the designing nowadays, or where designing is done. You plot then that in plots like that. And for example, this is the gain for one frequency point with regard to the input power and output power, but you can plot also the gain with regard to the frequency. I'm going to see if I can do that. If I remember where I PN. Let's plot this again with respect to input drive. If I plot with frequency. Okay. Oh well, we'll. Anyway, so you're basically using that to then characterize your device and see where the capable points that you can reach for your device are, and then you reflect that on what you've already reached. So if your reached gain is enough, or if you can reach even higher points. We learned some descriptions for parameters. The stability factor, which is a good stability factor, is related to the gain. If the gain peaks, your stability factor will dip. As we saw, if there's a dip in stability factor, there will be a rise in the gain. The rise in the gain means, hey, you have this standing wave is going around, going back, going forth, going back, amplifying, going forth, going back, amplifying, and so forth. And at some point, once it amplifies after a certain part, when we have this laterally diffused component, as we saw beforehand, here, for example, is that the diffuse component. At some point, this will start to have here a concentration of a high electric field, and that concentration of the high electric field will burn through the semiconductor, and will just burn your device, because it will be too dense of a concentration of the electric field that the device cannot handle. So the physical structure will simply tear. The physical connection between the atoms will rip. You will have issues with contact ionization and so forth. Then your device will just burn out. The K is a parameter that is dependent on the gain. K is good to the stability factor. K is used to define the stability. Above where is it? Above 1, you're unconditionally stable. Under 1, you're not unconditionally stable. So your device might start to oscillate. Yeah, and you have these factors. Basic interpretation of the MSG, maximal stable gain, as the GM over the CGD. So the parasitic capacitance between the drain source capacitance, the gate drain capacitance, the gate source capacitance, and how these parameters can be used to then derive what MSG and FT are. FT, once again, maximum current gain. That's why the GM was the ITS with respect to the VG, and the CGS, the gate source capacitance. Because of the VGS, you have the gate source capacitance there. So these are some parameters to remember, because these will be also asked in the exam. For what is the relationship with regard to MSG? What is MSG equivalent to with regard to the small signal model? And the important factor, as I said, is this to the upper right part, how the plotting of this chart, and then what FT and Fmax define, where you can find them, and what kind of slope they have. Yeah, and that's how the k factor is defined by the S parameters. So basically, these few slides in the end, these are important. Yeah, the rest will be taken by Professor Kwai. So yeah, that's the end of the lecture, I would say. Thank you very much, and yeah, if you have questions, we'll do that offline then.